Hello everyone, my name is Mahmoud, and today I'm going to present our work, Locality-Centric Data and Threadblock Management for Massive GPUs. This work is done in collaboration between Purdue University and NVIDIA. There's no doubt we have witnessed the rise of new emerging scaling applications. These applications exhibit high levels of implicit parallelism, which enables performance scalability, but only if compute resources can continue to scale. GPU in particular is a programmable accelerator that satisfies many applications demands and has been used to accelerate these emerging workloads. In this figure, we show the anticipated performance over scalable workloads if balancing GPU resources continue to scale, including the number of streaming multiprocessors and memory bandwidth. Over the last decades, and powered by the process technology advances, GPUs have successfully increased the number of SMs and transparently improving the performance by an order of magnitude. However, as we can see in the figure, these workloads still contain further parallelism to exploit and need more compute resources than what is available today to continue performance scaling. However, building a GPU with hundreds of SMs in a single monolithic GPU die will not be possible due to manufacturing hurdles found in small technology nodes. As we can read in the news, the largest three chip manufacturers are struggling with yield at 5 and 7 nanometer process technologies. This makes the GPU performance scalability at risk, as the next GPU generation will have low manufacture yield and will be very expensive to build at small technology nodes. To maintain performance scalability, proposals exist to aggregate discrete GPUs into a larger virtual GPU, as well as decomposing a single GPU into multiple chiplets to increase the aggregate die area. To maintain the same programming model and improving development productivity, the multi-GPU and multi-chiplet will be exposed as a single logical GPU to the higher software level. These approaches introduce non-uniform memory access and lead to decreased performance and energy efficiency if not managed appropriately. Transparently overcoming these NUMA effects will be a challenging problem for GPUs over the next decade. In this figure, we study the NUMA impact on a 4 GPU NUMA system when varying inter-GPU link bandwidths and topology. We evaluate the state-of-the-art NUMA GPU techniques normalized to hypothetical monolithic GPU performance that has the same number of SMs. The baseline applies round-robin scheduling and placement. The technique patch plus FT applies batch scheduling and first touch page placement policies. Kernel-wide partitioning partitions the whole grade and data in large chunks, whereas the CODA is a static analysis-based multi-GPU scheduling. To reduce the NUMA impact, we need to build almost 3 terabyte per second GPU link, which is very expensive and hard to manufacture. Ideally, we would like to achieve the same monolithic chip performance and remove NUMA impact with the cheapest possible interconnection. We observed that the previous work CODA outperforms other techniques and should be considered state-of-the-art versus other policies. However, there still remains significant room for improvement in the cost-effective and limited bandwidth connections. We qualitatively study state-of-the-art NUMA GPU techniques, highlighting their deficiencies. The previous techniques are either relying on first touch page replacement policy that can introduce a substantial performance penalty. Also, they may have limited coverage and do not exploit many common locality patterns found in GPU workloads. They work well for some locality patterns, but not for others. Third, they are not transparent and propose new APIs to the programmer. To this end, we proposed LADAM, a locality-aware data management for multi-GPU systems that address the previous work inefficiencies. LADAM has low overhead, it exploits GPU programming models patterns, and transparent. LADAM achieves this by exploiting a proactive static index analysis to optimize Threadblock scheduling, data placement, and cache policy. Now we will show an overview of our LADAM system. The figure shows an end-to-end overview of our proposed LADAM mechanism. First, we perform a symbolic offline index analysis in CUDA source code during the compilation process. Our analysis generates a locality table which is embedded in the executable. The locality table contains the locality type for each global data axis found in the kernel. Then during the runtime and on every kernel launch, the locality-aware scheduling and displacement component found in the driver reads the locality table along with the runtime configuration and the grid dimensions. Then the last decides the proper scheduling policy, data placement, and cache strategy to reduce off-chip traffic. Now we'll discuss each component in details, and we start with our static index analysis. The GPU programming model introduces new challenges in the design space for NOMA systems. The GPU employs hierarchical threading, in which the thread grid is composed of multidimensional grid of thread block, and each thread block itself is composed of multidimensional fine-grained threads. The CUDA programming model forces the programmer to use the hierarchical thread IDs explicitly to express the parallelism in the program. This is different from the flat, coarse-grained nature of CPU threads, where we have fewer coarse-grained threads do much more work than the GPU threads. In numerous GPU systems, threads are assigned to GPUs at the thread block granularity, not at the thread level. This, combined with the expressiveness of the thread IDs in the GPU program, an inter-thread block analysis must be performed to account for both the hierarchy of the grid and the dimensionality of the thread grid. So we propose Threadblock-centric index analysis, in which we create a one-to-one mapping between data and the thread block. We define the term data block as the region of data accessed by a thread block in each iteration of the kernel's loop. Data blocks are shaded based on the shade of the thread block that accesses them. For example, in this figure, thread block 0 accesses data block 0 and 2. The arrow here indicates the thread block motion accesses over the data blocks. Our index analysis idea is to break down index terms into prime terms, like thread IDs, constant values, and loop variables. And then we divide these prime components into loop variant group that contains all the terms dependent on the induction variable, and loop invariant group that contains all the remaining terms. The loop invariant group tells us the start position of the thread block. In this example, it contains block ID X, which indicates all the thread blocks will start from a unique position. Whereas loop variant group tells us the thread block motion over data blocks. We use some heuristics like the position of thread block IDs to identify the common locality patterns. Based on this index analysis, we classify the locality pattern into one of the following categories. First, no data block locality. In this pattern, thread blocks access exclusive data blocks with a stride in either X or Y directions, as shown in the figure. The second locality pattern is row and column locality, in which data blocks are accessed in either the row or column directions, and they are accessed by either a row or a column of thread blocks from two-dimensional thread grid. Making all these 2x2 combinations gives us 4 different sharing patterns. The last type is intra-thread locality, in which individual threads within a single thread block exhibit intra-thread spatial locality across regular or random axes. Finally, if the array index does not match one of these locality types, we leave it as unclassified and the default placement policy is used. It is important to note that because we do not do any data or code transformations, if our analysis does not match perfectly this pattern, it will not affect our program functionality, and it will just generate more off-chip traffic. The second piece is the runtime component last. As stated earlier, last decides the proper scheduling policy and data placement to reduce off-chip traffic. For no locality workload, the last schedules thread blocks in a large batch size to ensure page alignment. Dividing the batch size by the data block size tells us the minimum number of consecutive thread blocks that should be assigned to each node to avoid misaligning. Based on that, the batch size varies per kernel, as each kernel will have different data block size. For data, we use stride-aware placement. The previous work, kernel-wide partitioning, partitions data among the chip without considering stride information, resulting in significant off-chip access. In our approach, we use stride information provided by the compiler analysis to determine which pages need to be located on a given node, eliminating off-chip traffic. In case of row locality, the same row in the thread block grid accesses the data elements in the same row of the data blocks. In this case, we bind consecutive rows of the thread blocks and data blocks to one node such that the row-level data block locality is exploited. Similarly, for column locality, we bind consecutive columns of thread blocks and data blocks to one node. Some kernels will access multiple data structures in different ways. When this happens, each structure will be placed in the correct way. but there's only one Threadblock scheduler we can select for a particular kernel. For example, in matrix multiplication, the placement of matrix A favors a row scheduler, whereas the placement of matrix B favors column scheduling. And so in this case, we have a collision, and we have to pick a winner. To break the tie, we favor the scheduling policy that's associated with the larger data structure, because it will intuitively have more compulsory misses, and thus a bigger effect on off-chip axes, whereas the smaller, frequently accessed data structure have a greater chance of hitting in the local L2 cache. So in our example here, if matrix K is greater than B, we choose a row scheduling. For intra-thread locality that widely exists in data analytics and the graph traversal workloads, LASP applies coarse-grained data and the kernel partitioning to preserve data locality per thread. So in our example here, we partition both the kernel strip blocks and data into two large contiguous chunks over the two nodes. For the workloads that have irregular random axes and generate off-chip traffic, as shown in the right example, we applied an optimized cache policy. Our optimized cache policy is named compiler-assisted remote request bypassing. In our baseline, and similar to the previous work, the L2 cache is shared between local and remote traffic. So in this scenario, remote requests are cached twice, once at the L2 cache of the home GPU and another time at the L2 cache of the remote GPU that sends the request. In fact, cache remote twice policy can be beneficial in row and column locality workloads where remote requests are accessed by multiple SMs across the GPUs. However, the workload with intra-thread locality, caching request twice is a waste of cache resources, as the cache line is only accessed by one SM in the requesting GPU. So in this case, we cache remote request once as a remote node. We use our compiler index analysis to determine the locality type found in the program and apply the right policy. In the next slide, we show our experiment setup. To evaluate LADAM, we use GPGPU-Sim version 4 with the recent memory system improvement from Axel Sim Simulation Framework. The reason we use simulation is because the L2 remote caching and the inter-GPU cache coherence, among other features, are not present in the GPUs available to researchers today. So we evaluate our experiment in simulation. We also provide some results on a real hardware of NVIDIA DGX server. The results can be found in the paper. Our multi-GPU simulation system is configured to contain 4 GPUs connected by a switch. Each GPU is composed of 4 chiplets, and each chiplet has 16 SMs and one high bandwidth memory stack, and the chiplets are connected via the ring topology. We run LADAM on a selection of 53 workloads from different benchmark suites. Like prior work, we build the 53 workloads from all the benchmark suites and select only 27 scalable workloads that have enough parallelism to scale up on our simulated multi-GPU system. Then we discuss our experiment results. In the top figure, we show the performance of CODA and LADAM that combines LASP with CRP. All the results are normalized to the hypothetical monolithic chip performance. In the bottom figure, we show the off-chip traffic percentage. For no locality workloads, the LASP stride-away placement reducing off-chip traffic significantly compared to CODA. This off-chip traffic reduction is translated to 3x performance improvement on average. In row and column locality workloads, preserving row and column locality along with the input side awareness makes LADAM output from SCODA that applies fine-grained round-robin page interleaving that destroy row and column locality. In intra-thread locality, LADAM scores grain partitioning to preserve CSR graph locality along with cache remote ones improves the performance by 2x. Finally, in unclassified locality, LADAM's kernel-wide partitioning placement still improves the performance for some workloads. Overall, LADAM outperforms CODA by 1.8x on average and capturing 82% of monolithic chip performance. The reason behind the remaining gap between LADAM and a monolithic chip are complex indices that LADAM fails to analyze and irregular data-dependent excesses. To understand the efficacy of our compiler-assisted cache bypassing, we evaluated the performance effect of cache remote twice and cache remote once. Cache remote once improves the performance of intra-thread locality workloads by 40% or average, whereas it hurts the performance by 8% for the row and column locality workloads and stencil applications. So in our compiler-assisted cache bypassing, it takes the best of both policies by enabling cache remote once policy in intra-thread locality and remote twice policy in other locality patterns. Finally, in conclusion, due to the physical limitation of a chip and interconnect technologies, GPUs will have to overcome significant NOMA effects. We propose a locality-aware data management system designed to transparently overcome the NOMA effects of future hierarchical GPUs. LADM decreases inter-GPU memory traffic by 4x, improving system performance by 1.8x. As future directions, we believe that static analysis is the right direction to build cost-effective multi-GPU interconnects. However, we believe that there are still more opportunities to further customization to advance static analysis for strong NOMA GPU scaling. Thanks for you watching our presentation, and stay safe.